Hello, gentlemen. Thank you for joining. Hello, gentlemen. Thank you for joining us today for this webinar titled "Filament Winding: Efficient Material, Machinery, and Process Decisions," brought to you by CompositesWorld and presented by Engineering Technology Corporation, Toray Group. My name is Jeff Sloan. I'm the editor of CompositesWorld. Before we get started, I wanted to wish everyone a happy National Composites Week. You can see the National Composites Week logo here on the title screen of today's webinar. This is the second year of National Composites Week, and CompositesWorld is happy to be a part of this event again. For more information, please visit nationalcompositesweek.com. Now back to the webinar. This presentation will last about 40 minutes, followed by question and answer. If you have a question, you can type it at any time during the webinar in the question field of your GoToWebinar control panel. This webinar is being recorded, and when complete, will be made available to you via email from CompositesWorld. We have two speakers today. First is Jay Larson, General Manager at Engineering Technology Corporation. BJ has more than a decade of experience in the composites industry, primarily focused on the manufacture of material and process machinery. He graduated from the University of Utah with a degree in mechanical engineering with an emphasis on composites. Our second speaker today is Mel Singh. He's Product Development Manager at Engineering Technology Corporation. Mel has been working in the machine manufacturing industry for more than 10 years. His professional expertise is focused on designing control systems and application software used in the production of composite parts. Mel graduated from the University of Utah as well, and he obtained a bachelor's degree in science with specialization in software engineering. BJ, it's all yours.
All right, Jeff, thank you. And I'd like to thank everyone for joining and participating in the webinar today. If you look at the synopsis of what the webinar is going to discuss, I would like to just review it really quick, specifically the first sentence. We're planning on a high level yet informative look into how decisions made during the filament winding process can trickle down to affect final throughput. So a good starting sentence. If you read the rest of that paragraph, it seems like we're going to save the world, and we're going to do our very best to try. But for the most part, we're going to focus on decisions that customers make that can chain them into process efficiencies down the road. 3 years later, when you're in full production making parts, you can be tied to these early decisions. So that's kind of what we want to talk about today. We're going to shy away from heavy process decisions just because those are specifically they're pretty unique to different customers. So just covering our primary topics for the day. Key market drivers and industry trends will be reviewed. We'll look at part definitions and material selections, design and analysis, process and machine considerations, and what's next in filament winding. And through the course of the presentation, we'll kind of focus on efficiencies as we've discussed. So moving on, a brief history of Engineering Technology Corporation. I'm going to refer to it as ETC from here on out. We're more widely known as ENTEC Composite Machinery. We've changed our name in the last several years. We started in about 1962 as a result of the rocket motor industry here in Utah. We helped pioneer CNC technology within filament winding, and we also helped pioneer pattern generation software for filament winding. In 1999, we were purchased by Zoltech, and they were in turn purchased by Toray Group in 2014. And we're here today as a support and resource for the filament winding industry. And Toray and Zoltech also lend a lot of expertise and resources to our company. ETC has a unique vantage point. And as an OEM, we have a unique vantage in that filament winding has been around since the 60s, and so have we. We have worked with a large number of customers on a very large number of projects, and we've seen good examples of efficiency, and we've also seen bad examples of efficiency. So today, just as a preface, you probably need to know two things. Number one, I love clip art. You will be seeing a lot of it. And number two, that filament winding has had a long run. Again, it's been around for a while, and a lot of the efficiencies and process improvements have kind of been squeezed out of it. So, us being here 60 years later, we're kind of looking at those high level efficiencies. So I plan on sharing some tips that we've picked up along the way from customers and from our own research. However, we don't necessarily have a silver bullet that's going to improve every person's filament winding process, but they are out there. So moving on to the next slide. Again, clip art. Composites is a search for lighter and stronger. And as I said in the previous slide, it's been squeezed. So a lot of the low fruit, I guess I should explain the fruit real quick. Right here we see an image of the fruit tree of efficiency. And anyone who's familiar with the Six Sigma or other lean manufacturing principles has seen an image like this. The low fruit representing projects and continuous improvement efforts that have a low level of input effort with a high level of reward, and the high fruit being projects that have a higher level of effort with some diminishing rewards. So depending on where you are in the composites industry and how long you've been on it, what company you're working for, you may be trying to reach fruit on this tree in any of its various locations. We know that on the whole, composites are more expensive, more difficult to design, and more difficult to process than standard materials, i.e. metals and other things. But that's why we're in composites, right? We're looking for an edge that makes our company or our product more viable. The complexity of composites also lends, it can be a benefit at times because of its complexity. There's more room for efficiency savings all along the road to a finished product. So I want to briefly talk about industry drivers calling for efficiencies. Obviously, we're all on this call today because we want to be more efficient, or we're maybe learning in the industry and want to know how to get off on the right foot. There are a lot of positive changes going on in the industry right now. So there's a global fuel migration that automotive is spurring COPV technology. COPV being composite overwrapped pressure vessels for compressed hydrogen, or compressed natural gas. That should be CNG, and hydrogen. In addition to that, advancements in aerospace are pushing the search for new manufacturing techniques, trying to broaden our horizons just a little bit. And in doing so, there's just a wider adoption of composites materials in general. It's interesting, and it's rewarding to see them kind of starting to take hold. There are challenges as well going on in the industry. As always, there's rising production and material costs, and COVID, right? I'm not sure what permanent changes will result from the pandemic. I'm sure there will be challenges, but I think as a whole, we'll be able to adapt, and greater efficiencies is only going to help us adapt. This is a higher view of some of the challenges that'll require our attention and flexibility, just kind of related to the industry in general. I'm not going to get into all of it, but you know, some examples are social distancing and limited mobility can hinder sales. But an example of a benefit that could come from it, looking towards automation as a compensation for that limited mobility and limited working ability, might be an opportunity for many people within our industry. So there's a plus and a minus to all of it. Moving on to part definitions and material selections. We've, again, worked with a lot of customers, and all of those customers have had goals. Most of the time it relates back to what the boss is looking for. We want to maximize profit, or we want to gain a technological advantage. And that has, you know, kind of spurred the ongoing battle between managers and engineers. How do we increase profit, lower cost, and shorten lead times while still maintaining safety, quality, and performance? In the end, we want it all. We want to see these bottles lined up and just wait for the dollars to roll in after we sell them all, right? But in the beginning, we have an idea for a part. So we're going to start there. I want to talk just briefly about part definition. It can be a large hurdle, and it's also unique to each customer. So we're just going to assume that a part has been defined and that a reasonable business model has been developed. We know roughly how much material will be going into the part, how it will perform, and how well or how much it will cost. For this presentation, we're going to stick mostly with axisymmetric parts. Later on, Mel is going to do a design demonstration, and we will be using a Type 4 pressure vessel, which is a polymer-lined composite overwrap pressure vessel, as you see here in the picture. So, I just want to tell a quick story, and you can see our fruit tree of efficiency over here. It's got some low-hanging fruit. As you're getting into your parts, you know, we're going to have to buy tooling, and we're going to have to look at how the part is actually going to be made. We had a customer who was in the early stages of their developmental process, and they were purchasing a mandrel for a large tapered part. The aluminum mandrel cost about $5,000 more than the same steel mandrel for their part, and they looked to save a few pennies and bought the steel mandrel, and ended up having some difficulties extracting. So those few pennies that were saved purchasing the less expensive mandrel ended them up with several stuck parts on their mandrel. They could not extract the mandrel. It also ended up in extractor improvements, so they had to do more spending on machinery for their product, and it ended up in just a lot of headaches. So, you know, extending beyond this example, as I said, every part has tooling, and it needs to be carefully considered. And in the example that we are going to give of the Type 4 pressure vessel, the liners can be as complicated, if not more complicated, than the actual composite part itself, and they can have really big impacts on the overall performance. So, suggestion to anyone new into the business, a little bit of low-hanging fruit. Consult a pro. Talk to your material suppliers, talk to the liner suppliers. If you can round up consultants, just pick their brains a little bit. If you can possibly find a company that's already winding similar parts who's willing to share with you, get as much information on these little things that can trip you up as early as you can. It'll help in the process all along. So I'm going to pull up a graph. Many of us are familiar with it. It relates material strength to material density. And the material selection, you know, as I said, the part's already defined and we already know what's going into it, but this is just a consideration that should be made or commented on. The material selection is highly driven by your end product specification and your desired properties. As you start on the bottom end of this graph, we're down in the foams, so we're not very light, we're not very strong. Top end of this graph, we're very strong, and usually more expensive. So I do want to highlight that in all the range from foams to metals, composites kind of seems to be a small portion. It's just this little section right here. And even though it's small, there's a large variation of performance and cost, even within this small range. So this is a composites webinar. We know we're going to pick a composite material, but there are a lot of considerations that need to be taken into account during this that will affect your efficiency down the road. So we're going to kind of start with fiber selection, right? Most filament winders are using some sort of glass fiber or a carbon fiber in their processes. There are some more exotic fibers that are out there, but for the most part, this is what we stick with. Basalt is actually gaining some ground in the industry. And this can kind of be related as, you know, middle of the tree kind of fruit. It will have some impact moving along, but the selection process can be a laborious one. And it's not enough to just look at a spec sheet. We can go online nowadays, we can look at anyone's provided specifications, we can look at an ultimate tensile strength and a stiffness, but it's just not enough. I would encourage everyone who's looking into composites or a new composite part to get the strength variation data for the material that they choose from the supplier. If you can lower your variation or pick a lower variation product, your design knockdowns are going to be lower, your part weight will be lower, and your throughput will ultimately be higher. Or at least your cost will be lower and your profits will be higher. I would encourage that we get samples and run them in a similar arrangement to your process. And I have a slide after this that will show how we did that for a customer. And if you can afford it, make prototypes, several if possible, and close the design loop. Mel's going to talk a little bit about how this design loop works, and we'll elaborate more on it in the future, but these are all important parts of the process. On the screen now, you'll see the fiber selection. We did some winding trials for a customer. We set our tensioner and our resin bath up in a similar arrangement to their filament winding machine, and we ran several fibers on the equipment that they were going to be using. We were watching, let's see if this video works. We were watching how the fiber paid off, how it went over rolling contact points, how it behaved in the resin bath. And you'll see, if you watch very closely, there's a little bit of fiber buildup here on one of these rollers. This is exactly what the customer was looking for. In comparing the different types of fibers, they were able to make a better decision on which material went into their product. You'll see on the right side, we also ran it over some static contact points in efforts to quantify the effects of the fiber on their process. So if you can, get a hold of the equipment. This is a pretty critical step in the process. Resin considerations. Resin selection is certainly medium difficulty if we're looking at the fruit tree of efficiency. There are so many things to consider, and it is incredibly customer specific. So I'm just going to touch on highlights. Resin storage, preparation, and mixing processes should all be very carefully considered. They can run away on you very quickly, both in terms of footprint within your facility and in terms of dollars when you're hiring people to do some very complicated processes in the mixing. Things that should be considered that aren't necessarily thought of at the onset was how well does the resin clean up? What types of solvents are required? Will environmental regulations come into play if you're storing large batches of these chemicals? And what PPE is going to be required to keep your employees safe while they work with them? These can all be cost drivers, and they can very much affect the end product cost. Cure times and cure methods are also impactful in your process. They will define what kind of curing equipment you have, what kind of storage, if you'll need refrigeration for storage. And again, they can be big drivers in equipment cost and labor cost as you're making your parts. And in the end, surface treatment, sizing, resin compatibility are all big factors. This is all information you can only get from the suppliers normally, and it's information that, again, you can't just look at a spec sheet and trust it. The fibers and the sizing might have different interactions with resins that you don't anticipate. So if we can suggest getting a sample and doing mechanical testing of both laminate and neat samples, and making sure that you're selecting the right materials for your process. Right here, you'll see a small filament winding machine with a flat plate on it. We've used this extensively to create laminates for this type of mechanical testing. And it can be made without having the ability to make Towpreg. It can be made just with either some prepreg tape or some Towpreg, or even a wet winding bath can be affixed to this. But it'll give you good, solid data to vet your resins with. This brings us to kind of a hot button topic within the filament winding industry, wet winding versus Towpreg. So I'm just gonna play this little video for a second. You'll see, again, the fiber paying off. This is a dry fiber, and it's coming off of our tensioner. It's going through a redirect, and then it is going on top of a drum that's soaked with resin. That resin is then impregnating the tow, and the resin has to be of low enough viscosity to actually penetrate the tow. So we're typically dealing with relatively low viscosities so that it can penetrate in a short amount of time. The downside to that is that once it gets onto a winding machine, it can come out of the tow just as easily as it can go in. So running at very high speeds with a wet winding process is not possible. It typically tops out around 1 meter per second. Any more than that, and you're looking at resin coming out of your part, which isn't bad for a lot of cases, but if you're looking at very high winding speeds, it's difficult, and we would suggest moving to a Towpreg. So Towpreg is an uncured resin-filled composite tow that eliminates the need for a resin bath. It also disconnects your winding process from your resin impregnation process, so they become two separate processes, which can give you more flexibility. The resin that is in, the resins that are pre-applied in Towpreg are typically of higher viscosity than wet winding, which allows for much higher winding speeds, on the order of 3 to 5 times that of wet winding. So wet winding versus Towpreg, what would we suggest? When looking at wet winding, there are some positives. They're low cost, they're widely available. You get to control your own resin content, and they're flexible. You can try several different types of resins with several different types of fiber, relatively easy. Cons are the cleanup. It is a messy process. You have lower winding speeds. Your resin content and control is also a negative because you have to control that on site. And the mixing and storage of the resin and the chemicals associated with it can be a burden. Pros for Towpreg include less cleanup, much higher winding speeds, lower variability within the product. Most Towpreg manufacturers will quote very good the variability on resin content, tow width, and other factors. So low variability. There's no on-site resin mixing or storage to deal with. So it greatly reduces the footprint required to run your product. The cons, however, are a higher cost. Now, on an individual basis, companies have to decide if that higher cost outweighs all of the cons that make up the wet winding. But that's for an individual company to decide. There's lower flexibility. Once you've bought the product, you can't change its width, you can't change its resin type. Another factor is, these products may not have the cure profiles or characteristics you want from your resin. So it might be required that you work with the material supplier to fine tune something. So there's definitely a little bit more difficulty involved with it at times. Just to cover these pictures real quick, this is a tow, dry carbon fiber tow that was then converted into Towpreg, and you can see it's very uniform width, uniform thickness, and a uniform resin content. So it plays better in the sandbox, if you could say. This is a carbon fiber Towpreg product, and this is a fiberglass Towpreg product. Most products are available just depending on who you talk to. Sorry, one other con I missed. Towpregs also have a more complicated fiber path. They require a lot more rollers. The tow must remain flat through a bunch of changing directions, and that can stack up your complications pretty quick. Okay, so I'm going to turn the time over to Mel. We're going to talk about design for a few minutes, and here he is.
When it comes to part design, there are multiple approaches and methodologies that an engineering team can use to design a particular part. Rather than go through each approach and their individual advantages and disadvantages, I will instead focus on high-level elements common among all approaches and a tool designed to streamline the entire process. The part design process begins with a selection of part geometry and material based on application requirements. These requirements take on the form of physical, mechanical, and economic properties. The products of the selection process are the mandrel geometry and composite material, which combine to form a conceptual laminate. The conceptual laminate is a geometric description of both the mandrel and the oriented plies stacked upon it. It represents a potential design for the part and must be tested and proven to be viable for production. The testing and proving of a conceptual laminate occurs in proving loops structured to refine the potential design. Of these two loops, the inner loop, the FEA loop, consists of performing finite element analysis on a representative model of the conceptual laminate. Depending on the constructed FEA model, different failure points and modes can be quickly identified and translated into refinements to the laminate. For example, the FEA results may indicate that a region in the model requires additional reinforcement. The laminate can then be modified with the addition of another composite layer, and this refined laminate model can then be subjected to further FEA. The FEA loop is a cost-effective process that converges on supplying the outer proving loop with a prototype to test. The prototype loop, in contrast to the FEA loop, can be both costly and time-consuming to execute, as it involves the manufacture and mechanical testing of batches of prototype parts. A prototype winding program will need to be generated based on the conceptual laminate to manufacture the prototype. The manufactured prototype will then undergo appropriate mechanical testing to prove the viability of the potential design. The criteria used to test the prototype is very much application specific. To close the loop, critical refinements can be made to the conceptual laminate based on the resulting test data. Once a potential design has successfully gone through the proving process of finite element analysis and prototype testing, it is then ready to undergo production optimization before entering full-scale production. Keep in mind that I'm omitting the process of certification, as this is very much also application specific. Looking at the entire process, the entire design process, it is clear that the conceptual laminate is central to all aspects of the process. It is only natural then that the biggest efficiency gains reside with the generation and processing of the laminate. The use of software tools to not only generate the laminate, but construct the FEA model and output winding patterns can greatly aid in this purpose and represents the low-hanging fruit on the fruit tree of efficiency. One such tool is ETC's in-house winding program generation software, FiberGraFix. FiberGraFix streamlines the design process by making every interaction with the conceptual laminate intuitive and seamless. Creation of the mandrel geometry is as simple as importing a 2D DXF file. As shown here, a 2D DXF file generated in a CAD package is being imported. With a few definition clicks, selecting the profile and center line, a 3D representation of the mandrel is created. Easy definition of the conceptual laminate is possible simply by adding a layer to the conceptual laminate, selecting the pattern type, in this case a hoop, defining the surface area to cover, selecting the number of plies, in this case 2, and accepting the generation parameters. Likewise, a 20-degree wind angle helical can be created by adding a layer, selecting the closed pattern type, defining the surface area to cover, and specifying wind angle constraints, in this case 20 degrees from tangent to tangent. The wind angle constraint guarantees that the calculated fiber path will have a 20-degree wind angle from tangent to tangent while allowing for a turnaround on both ends to complete the winding circuit. FiberGraFix contains powerful friction modeling tools to indicate the potential of fiber slippage, therefore removing some of the trial and error involved in winding program generation. As you can see on the screen, the fiber path is shown with both axial and diameter positions and the calculated wind angle. You'll notice that from tangent to tangent, 20 degrees has been affixed to the wind angle. Once a conceptual laminate has been defined, here's a visualization tool displaying the wound 20-degree helical layer, as it would appear on the mandrel. Tools such as this help us visualize any changes that are made to the layer. Once a conceptual laminate has been defined, it can be exported to the FEA interface package, which acts as a bridge between FiberGraFix and the chosen FEA software. This can be accomplished by simply clicking on the Output FEA button and saving the data file. The resulting data file can then be imported into the interface. The user interface is intuitive, such that clicking on the model allows you to examine the properties of each ply, segment, and region. Properties such as the wind angle, the thickness, ply stacking, and orientation. The lamination schedule can be redefined as desired by simply dragging and dropping the constructor pane. The completed FEA shell model can be output by selecting the FEA package format. In this case, NEI Nastran, specifying some output parameters, and clicking OK. Additional FEA support packages are being developed. At this point, the FEA analysis is performed on the shell model, and we're going to assume that based on the results, further refinement of the laminate is required. This is possible by simply changing the generation properties of a layer, or in this case, adding a new helical layer and moving it into place. This reinforcement helical will begin and end an inch below the cylindrical section, a knuckle winding, so to speak. As you can see here in the visualization tool, the complete fiber path has been calculated, and it is indeed an inch from the tangent. FiberGraFix also contains industry-leading machine motion editing capabilities in the form of EDPAT2. Through its use, the winding program can be optimized to reduce wind time, improve motion stability, and smoothness. It also has the ability to simulate the execution of machine motions as shown. All these features and more streamline the part design process to ensure you get from concept to production as efficiently as possible.
All right, thanks, Mel. I just wanted to add a few points. This process that Mel just reviewed can be laborious. There's a lot of back and forth. There's a lot of engineering, but the room for efficiency savings is huge. If you can shorten your wind times, 1,000 bottles later, you'll thank yourself. And if you can remove a single ply from the process by optimizing this design like Melvin has shown, 1,000,000 bottles later, you're going to be thanking yourself. So it's a long, kind of tedious, very efficient section of the process. So thank you, Mel. We're going to jump into process and machine considerations a little bit. I'm going to have to pick up the pace. A lot of times, let's see. The only items we're going to talk about on process is really layout, okay? I didn't have any customers that were comfortable having their shop floors shown on a webinar, but as I stated earlier, I like clip art very much. We're going to utilize it. As an OEM, we've been in a lot of facilities. We've seen every layout under the sun, and some are good, some are bad. This can be low-hanging fruit if you're starting from scratch. So I'd encourage anyone who's just getting into this to very highly consider your layout. Looking at this, you can see that the docks are down below. They go right into material storage. For this particular customer, process 1 was filament winding, then process 2 was curing. There was some extraction and some post-processing, and it came right back out to shipping. It was very slick. If you're a customer that's been in this for a while and you're trying to adapt to existing equipment or a new process to existing equipment, it can also be very challenging, and it can be high fruit on the tree of efficiency. Our only comment here is that this should really be considered a one-way street, and trying to keep it that way will save numerous headaches down the road. This, I'm showing the bad example second, but this is also an actual layout for one of our customers. Despite the seeming simplicity of the layout benefits, we see this process flow quite often. And the only efficiency suggestion we really have to give to customers like this is where to put the traffic signal. It can be very messy, and definitely once these pieces of equipment are down on the floor, they're very hard to move. So pay close attention. It can be a real mess. We're going to jump into machine selection. Our machines and filament winding in general manufactures a very wide range of parts, from small scale sporting goods to very large scale complex items like rocket nozzles and gas tanks. To do the wide range of products, a wide range of machinery is required. In the market, there are small 2-axis machines that will wind small parts and do test samples. And then there are large scale machines. This one in particular will run 60 to 100 toes, has a 10-inch rotating eye, and can handle a mandrel up to about 20,000 parts. So a lot of different options with machinery. All these options that we're looking at right now are actually standard options, which means that their costs are a little bit lower, as long as their parameters fit within your part anyway. So this machine here on the left, we have customers that are looking more toward production. We have 5 spindle machines that help accommodate that. The 5 spindle on the left is our economical option. The one on the right that you can see supported top and bottom has dual drives on all carriages and can operate much faster. It is called the CXG, and we're going to come back to that in just a little bit. I just want to talk briefly on the selection of axes for a machine. Sometimes these get a little bit confusing. You'll see a part sitting in this machine. The rotational axis that's controlled by the chuck is our A axis, and it's often referred to as our spindle axis. The X axis, which is longitudinal down the part and is our main carriage, is usually referred to as the horizontal axis. And these 2 axes give you a lot of capabilities for cylindrical parts, very long, incomplex parts. But as soon as you start getting into more complicated shapes, i.e. tanks with domes, and you're looking to control your fiber band around the domes efficiently and easily, you need more axes. So we typically add the Y axis and the B axis, which gives you radial motion in toward the part and also a rotational motion of your delivery head. Some customers even go toward a C axis. You'll see our tree again. A C axis is referred to as yaw, and it's only used by customers typically who are trying to keep Towpreg very flat around a large dome, and it's definitely on the higher end of the tree. Basic machine process improvements during your selection process can be made. These are low-hanging fruit. This picture displayed is one of our cat creels. It has magnetic particle brakes inside that control tension. It does not have rewind. We've had customers that have upgraded from this type of creel to a servo-controlled creel and have gone from failing burst tests on hydrogen tanks to passing. So just the addition of better controlled tension in this process can greatly impact the viability of your product. Other improvements in your creel are minimizing contacts and increasing fiber strength. The resin bath has options for improvement as well. A lot of customers will run just a straight dip bath. Drums will actually provide a little bit better resin control over the dip. And as we spoke about earlier, you can eliminate the resin bath altogether and just run Towpreg. The machine improvements are simple and obvious. If you want to improve production, you can add spindles, you can upsize motors, increase toe count if your product design allows for it, and smoothing patterns, as Mel spoke about. A lot of our customers are only interested in making one part and making many of them and doing it well. For those customers, we would suggest a traditional filament winding machine. A multi-spindle machine will allow you to run parts simultaneously and obviously increase your throughput. So really good options for high volume production. But we also have customers that aren't looking for high volume, they're looking for higher flexibility. They could be a job shop, they could be a facility that does a lot of prototyping and doesn't necessarily know what they're going to be winding from one day to the next. And traditional filament winding machines are not flexible in these applications. Robotic winding machines have the ability to run several types of mandrels and several types of materials in any arrangement you can imagine. These tailstocks are very easy to move to accommodate larger parts, and the robot can even be placed on a carriage to allow you to lengthen the machine. So again, very flexible, very cost effective for the customer that's looking just for flexibility. What's next in filament winding? If you're a pro, everything I've kind of shared, you've probably already seen. Your companies are already doing it. So what's changing and how do we reach the high fruit on the tree? Automotive is causing the automotive industry and the global shift toward compressed natural gas and fuel cell vehicles has spurred a lot of advancements in composites. The four main topics of conversation that we've had from not only automotive customers, but aerospace and even others have been as follows. People are starting to look at structural components. People are looking at work cell automation. This one's not necessarily new, but it's becoming a hot topic. People are, of course, looking at high-speed filament winding. And many are just wondering what's beyond filament winding. How do we generate these parts without a filament winding machine? So structural winding components, this is actually a really unique field that's just kind of been emerging over the last year and a half. These pictures are all from CompositesWorld. The robotic winding that we discussed earlier allows for the creation of non-axis symmetric parts. So you'll see here a chair and a few other structural components that are being generated. And it's very new, and it's opening a lot of doors in the automotive and aerospace industries. Work cell automation. Obviously, as with any process, if a customer is looking for very high throughputs and has the money to spend, this is a possibility. Automated processes are kind of there in the left. You can see they include part unloading, curing, auto tie-on, cutoff, inspection. You'll see a work cell that we've worked through as a prototype with some customers. It has 8 servo creels, 4 CXG winders, and will conservatively produce about 700 hydrogen tanks per day. So that's fast, and customers want fast. So I want to just rewind a little bit to 2019. I'm not a huge fan of 2020 thus far, but back in 2019, it seemed like we kept hearing the same question. People wanted the fastest filament winding machine in the universe. Okay, so we heard time and time again that we want 5 meters per second out of our machines. We want to run fast. We want to have very high throughputs. So what is the fastest filament winding machine? There are several out there. We have our fastest is called the CXG, and we have competitors also that have some filament winding machines that'll do 5 meters a second, and it's an advertised speed. And is that the fastest? And I would say yes. Most of these machines, ours and our competitors, run about 5 meters per second on hoops, but all of these machines slow down to around 2 meters per second or less on the helical winds. As this carriage starts oscillating back and forth and the rotating eyes move in, there's a lot of inertia. And typically this horizontal carriage, as soon as it accelerates up to speed, it's starting to decelerate because it's coming to the end of a part. So there are some real world limitations to filament winding speed. All of our competitors and us, we're all using off-the-shelf motors. Material packaging, tensioner capability, and safety are all limiting factors to these fast machines. So while we're pushing the boundaries of all the equipment we have, there are some very practical limitations to running these speeds. And which begs the question, should we be looking at linear fiber payout speed as a measure of efficiency? If you come to us and you say you want 5 meters a second, our next question is going to be, how many toes are you running? How much material are you actually putting down? And what are your goals? I think, looking at those original slides of what the bosses want with the carbon fiber all lined up out the door, our bosses want to see parts per time per dollar. And to get there, speed is a very important factor, but so is every other consideration above this slide. If we've chosen the right materials, if our design is spot on, if our process is laid out well, and if we have automation and the fastest filament winders in the world, you're going to be doing very good. So, but what comes after that? A lot of customers have asked. So what's beyond filament winding? I think it's collaboration. It'll be the growth of our composites community that's going to increase composite adoption and drive process and equipment improvements. And those improvements might not look like filament winding. They might not look like anything we're doing currently, but they will serve the industries that we use as customers. An auto manufacturer that I can't mention and a material supplier that I also cannot mention have proven this. They have gotten together and through their test methods, through their design methods, and the supplier's willingness to create products that the automotive manufacturer needs, they've reduced their COPV weight by over 10%, which is phenomenal. Very much world-class, and I think you'd probably be surprised at who these manufacturers are. They're not the ones in the limelight necessarily, but they are doing good, and they're doing it because they're collaborating. So ETC is excited to lend our expertise and resources to the conversation. We hope it continues, and I would like to thank everyone for their participation. Do you have any questions?
All right, thank you, BJ. Thank you, Mel, as well. So we have a few minutes now for questions for our presenters. So attendees, if you have a question, please use the question field right now on your GoToWebinar control panel to put a question to our presenters. And let's go ahead and get started. The first question is this. I am pretty interested in the 5-spindle filament winder, but do you have any mandrel handling systems as well? This plays a major role in production time.
We do. We are a FANUC robotics integrator. We've made applicator ends that will actually unload and load a 5-spindle winding machine. So the answer is yes, we do.
Right, next question is this, second. What kind of control systems do you use on your machines? Which one would you recommend and why?
We have 3 that we use. We have an in-house one that we call WiMAX, and it is compatible with Windows 10. We also use Siemens and we use FANUC. FANUC is has very short lead times. I can't say which one we prefer necessarily. All of our customers make that decision on their own end, but we supply all 3 of those. Some lead times are more long than others, and some costs are higher than others, but those are the ones that we offer.
All right, next question. The FiberGraFix software seems pretty powerful. What is the software model you use for it? Is it token-based, and does it come with the machine?
I'm going to defer to Mel.
It is token-based. It is an additional cost to the machine. Please contact our sales department, and they'll obviously give you a quote. But yes, it is a item of its own on the machine.
All right, here's a related question. Do you sell your software without the machine?
Of course, yep. We sell several licenses a year. It'll work with other customers' filament winding machines as well.
All right, next question. What would you consider a normal winding speed?
With a wet resin bath, normal winding speeds are about 1 meter per second. So somewhere in the 30 to 40 inches a second range without spatter. Towpregs can get up an average pattern with helicals and hoops will run about 3 to 4 meters per second.
All right, next question. Is there a limitation for the size and weight of a part to be wound? Considering long mandrels with big diameters, is it possible to use intermediate supporting structures to help the winding process without impairing the quality of the wound part?
We do have customers that have supports. These customers are running products or parts that are about 50 feet in length. They're narrower parts, so they do have some whip. In the middle, they sag while they're winding it, and they do have a rest that comes up. It has very broad rollers, and it does support the part. Now, they don't see a huge impact on their part strength overall, but they don't have a really high strength application either. So to try and answer your questions in order, we do have machines that'll do very long lengths and very heavy weights. We prefer that the mandrel can support its own weight and the tensions generated by the fiber winding by itself. But you know, you were talking about custom applications, and the sky's kind of the limit.
All right, next question. Do you sell machinery that can handle thermoplastic Towpreg?
We have not produced any commercially yet. We have looked at the lasers and lights and the other heat sources that are required to soften the thermoplastic for winding, and we would definitely be, willing to start a project like that.
All right. I forgot the very first question, which was about whether or not your presentation will be available as a PDF.
It will.
Can you address that? Okay. All right, next question is this. How much does equipment for filament winding typically cost, including winder, creel, et cetera? And I realize this is a broad question, but maybe you can give us some ballparks.
I'm going to give you the middle of the road. So a 5-spindle filament winding machine with associated resin bath and tensioners to run those 5 spindles for, like, let's say a medium-sized part is going to be ballpark, all that equipment together, somewhere between $400,000 and $500,000. Now that's just that's very ballpark.
Okay, so $400,000 to $500,000.
Yeah, it's it can be lowered, especially if we're doing standard machines. That's a tough question to answer.
Yeah.
But obviously we have machines that start at about 30,000 for the test winders, and they go all the way up.
All right, next question. Do you have capability to strip separator film from slit tape prepregs?
We do, and we have a small tape head application, something similar to an ATL or a fiber placement head design that we have used for some customers using a slit tape.
Okay, next question. Does FGX help identify how many layers I have to do as per different pressure ratings? And I'm not sure what that means. I'm hoping you can parse that.
Unfortunately, it does not. FGX is strictly a laminate generation tool. So outside of if you look at the design process itself, outside of that, in the material selection and mandrel geometry definition, that is where those constraints would be applied. So to the answer to that, unfortunately, is no.
Okay.
You could use the output though and reiterate, right?
Absolutely. Okay. So like I mentioned in the presentation, the position that FGX sits in is in between the FEA software and the filament winder. So anything that goes or comes out of FGX would then plug into your FEA software, whereby you would essentially determine how many layers you need, what angle these are, how many reinforcement layers, so on and so forth, and then plug that information back into FiberGraFix.
So question asked, you could easily verify whether or not a pattern adjustment would handle more pressure.
Okay. Next question, can you control fiber tension as delivered from the final payoff?
Yes. Depending on the machine creel arrangement, our machines can actually talk to the tensioners, and those tension values can be set up in your patterns.
More to that point as well, we have built machines where the actual tension measurement sensor is in the delivery itself. So we would be measuring tension at the point of delivery. Yes.
Okay, next question. Do you have different types of resin impregnating systems for wet winding?
We typically just offer dip baths, which is a series of bars that the fiber will go over and down into a bath of resin. We have drum rollers where the fiber will go over a drum that has a film of resin on it, and then we handle Towpreg delivery. But those are the only types of impregnation processes we have. We do know of customers that do a delivery head type impregnation, so the fiber and the resin would meet at the machine somewhere near the delivery head, and the tow would be impregnated with greater control than a resin bath. But we don't have any of that technology. It's being worked on.
All right, next question. Do you have the ability to monitor and change pressure of type 4 pressure vessels during the winding process?
Yes, we do.
That was easy. All right,
Yep.
next question. You mentioned in the presentation the tensioner shown does not have take up. Do you make tensioners that do?
Oh, we certainly do. So if you go to the website and select a filament winding machine, down below you can look at the accessories that are available for that filament winding machine. We offer the more basic cat tensioning systems, and we also offer servo controlled options. It's called the ST2, and it is commercially available.
Right, next question. Can you deliver complete delivery heads for Towpreg?
Yes. Often. Sorry, easy question.
Next question. When would I need to use a YAW or yaw axis?
Kind of as I mentioned in the presentation, yaws are only used by our customers making very complicated parts. The fiber will come in, and if you're going over a large dome and want to keep that fiber very flat going over that dome so you can control your buildup and your consolidation, you would use a yaw axis in that application. It does complicate the fiber delivery quite a bit, but they are available.
Right, I think we have time for one more question. And it is this: I have another brand of filament winder. Can I switch to FiberGraFix to generate my part patterns, or should it be your equipment? I think you kind of answered this already, but I'll let you take this now.
The answer to that is absolutely. FiberGraFix has the capability to output winding programs to any filament winding machine, be it our own or our competitors. It is filament winding independent.
Okay. All right. Well, BJ and Mel, we are very close to the top of the hour. We do have some questions that we were not able to get to. Actually, we have many questions we weren't able to get to. So I want to assure attendees that those will be saved and forwarded to BJ and Mel to be answered offline. So Mel and BJ, I appreciate you giving this presentation today. It was very interesting, and thank you very much for it.
No, thank you guys.
Thank you.
And thanks to our attendees for joining us today. We appreciate you being here, and we hope you'll join us again for the next CompositesWorld webinar. For more information, please visit compositesworld.com. Again, happy National Composites Week, and have a good day, everyone. Bye-bye.